Welcome to this talk about Approximate Turing Kernels. I am Astrid Pieterse and this is joint work with Eva Maria Holst and Stefan Crouch. So to define Approximate Turing Kernels, let me start by talking a little bit about kernelization. So kernelization is a way to basically formally define the idea that you may want to pre-process a hard given problem before trying to actually solve it. So a kernel is a polynomial time algorithm that takes some instance of a parameterized problem and outputs a new instance of this parameterized problem, whose size is bounded by some function of the original parameter, and of course these two instances need to be equivalent. Now of course the goal is to obtain kernels that are small, meaning that this function f here is small. But we can show that for some parameterized problems there are actually no small kernels, in the sense that there are no kernels of polynomial size. Of course we don't want the story to end there. So people have been looking into several generalizations of kernelization. For example, instead of only producing one single new input instance, we can look at Turing kernelization, where it is allowed to produce multiple instances. On the other hand, we can try to relax the fact that the new instance has to be equivalent to the original instance by looking at approximate kernelization. And in this talk, we will combine these two notions and define approximate Turing kernelization. But to do that, let me first define Turing kernelization and then define approximate kernelization. Okay, so a Turing kernel is a polynomial time algorithm that solves the problem when it's given access to an oracle that actually solves instances of your problem, as long as these instances are small, meaning that they have size bounded by some function of the parameter, and this function is also the size of the Turing kernel. Okay, so Turing kernelization generalizes normal kernelization in the sense that you could just, in polynomial time, run the kernelization algorithm on the input instance, obtain a preprocessed instance, and give this preprocessed instance to the oracle. Now, of course, this preprocessed instance is small because we ran the kernel, and then we can simply output whatever the oracle outputs. But Turing kernelization is much more general than that. One could even produce some small instance after some polynomial time preprocessing, give it to the oracle, and based on whether the oracle says yes or no, produce a new instance, give that to the oracle, etc., etc. Okay, so that is Turing kernelization. Now let's have a look at approximate kernelization. Okay, so to think about approximate kernelization, first of all, we need to move away from decision problems towards optimization problems. So the first thing I want to think about is what would just an exact or one approximate kernel look like? Okay, so first of all, it's still just a kernelization algorithm, and we still have that the preprocessed instance must be small. But the question is how to define when the preprocessed instance is equivalent to the original instance. And to do this, a kernel must always come together with a solution lifting algorithm. This is another polynomial time algorithm, and what it does is it's given the original and the preprocessed instance and a solution for the preprocessed instance, and then it can lift this solution back to a solution of the original instance. And as long as you're not talking about randomized kernels, you can always safely assume that this solution lifting algorithm simply has access to all the steps taken by the kernel, because it can simply mimic them in polynomial time. So the absolute minimum requirement would of course be that if I give an optimal solution to the preprocessed instance, then the solution lifting algorithm is able to give me an optimal solution for the original instance. But in fact, for one approximate kernel, we require just a little bit more. If we're given a C approximate solution for the preprocessed instance, we also want to receive a C approximate solution for the original instance. Now, what you see here is that if you have a kernel for a certain decision problem, it's not immediately a given that you also have a one approximate kernel for sort of the naturally corresponding optimization problem, because you need to have this solution lifting algorithm with this guarantee. I think for most kernels you can prove that the solution lifting algorithm exists, and in fact often the correctness proof of the kernel immediately gives you one, but this need not be the case. Okay, now for an alpha approximate kernel, we slightly change the definition to say that if we're given a C approximate solution in the preprocessed instance, we only have to guarantee that the solution lifting algorithm can give us an alpha times C approximate solution for the original instance. Okay, so we can lose a factor alpha in this step. Okay, so now that we've seen Turing kernelization and approximate kernelization, let's combine them into one notion. So an approximate Turing kernel, just like a Turing kernel, is a polynomial time algorithm that, given an input instance, will output now not yes or no, but actually an alpha times C approximate solution when it's actually given access to a C approximate oracle, and the size of instances that it gives to the oracle need to be bounded by some function of the parameter. And this function is, as usually, the size of the approximate Turing kernel. Okay, so this C here is something actually that the algorithm does not have access to, just like a C approximate kernel would not have access to C. So in this way, we guarantee that approximate Turing kernels actually generalize both approximate kernels and Turing kernels. So when does it make sense to look for an approximate Turing kernel for your problem? Well, first of all, the problem needs to have an alpha approximation algorithm that runs in FPT time. That means it runs in time bounded by some function of the parameter times some polynomial in n. It's easy to see if you have a problem and it has an alpha approximate Turing kernel, then it also has an alpha approximate algorithm running in FPT time, because you can simply run the Turing kernel and replace all calls to the oracle by any algorithm that will solve the problem. At the same time, if your problem has an alpha approximation algorithm, it trivially has an alpha approximate Turing kernel, and there's not much left to do. Also, since approximate Turing kernels generalize both Turing kernels and approximate kernels, naturally, if you find an approximate Turing kernel, you would want the size bound to be better than the size bound on the best known Turing kernel. And you also want that the size bound is better than in the best known alpha approximation kernel, or maybe you can get a better approximation. Ideally, in both cases, you have some evidence that the best known Turing or alpha approximate kernel cannot be improved. Okay, so with that in mind, let's have a look at our results. So we studied a number of graph problems when parameterized by the parameter Treewidth, which I will get to in a minute. So we show that they have 1 plus epsilon approximate Turing kernels for all epsilon larger than 0, where we assume that a tree decomposition is given on input. If it is not given, we can approximate it, but then these bounds will get slightly worse. We also have a general statement that says if a problem is what we call sufficiently friendly, then it also has a 1 plus epsilon approximate Turing kernel of a certain size. Now in this talk, I will talk about the Turing kernel for independent set and for connected vertex cover. Okay, so let's have a look at the checklist basically. So all these problems are FPT parameterized by Treewidth, which easily follows from, for example, Courcell's theorem. Furthermore, it's always hard to find polynomial kernels parameterized by Treewidth. Often there's an easy proof saying that they do not exist. In particular, for example, vertex cover and independent set, you can easily show that they are MK2 hard, which basically means that it's very unlikely that they have polynomial Turing kernels. Also, there are no good approximate kernels known for these problems, and actually we answer an explicitly asked open question by a paper in Stock 2017, which asked for approximate Turing kernels for the independent set problem parameterized by Treewidth. On the other hand, we also don't know for any lower bounds, so it's actually possible that an approximate kernel might exist. Okay, so now let's say a little bit about Treewidth. So Treewidth is simply the width of the best tree decomposition of our graph. And a tree decomposition is a tree with a number of nodes, and each node has an associated bag. And a bag is just a subset of the vertices of our graph G. And then there are a number of requirements. First of all, for every edge UV in our graph, we need to have that both U and V are contained in some bag. So for example, if you see the edge UV here, you see that there is a bag with U, V, and V. Furthermore, if we look at any vertex U, then if we look at the nodes that contain U in their bag, then they must form a connected subtree. For example, if we look at all the nodes containing B, then they form a connected subtree. And lastly, every vertex needs to occur in at least one bag. And the width of a tree decomposition is simply the size of the largest bag minus 1. Now for a little bit of notation, if we look at a node T and at all the vertices that are in the bag T or in the subtree rooted by node T, then we denote the graph induced by these vertices by gt. Finally, I want to mention an important property of tree decomposition. So even if you don't know Treewidth, what is basically all that we will need is that Treewidth gives you nice separators. So for example, if we look at the bag containing UVW here, and we look at UVW in graph G, then we see that if we remove them, they separate G into several components, and the same is true in the tree decomposition. So the nice thing about graphs with small Treewidth is that they have small separators and often small balanced separators. Okay, so let's have a look at the approximate Turing kernel for the independent set problem. So we show that the independent set problem, when parameterized by Treewidth, has a 1 plus epsilon approximate Turing kernel that has order L squared over epsilon vertices. So the size of the kernel would be at most L to the L squared over epsilon squared. So the plan is as follows. First of all, we're going to find a separator in our graph, and that separator is going to separate the graph into two pieces, A and B. Now we will do that in such a way that part A is quite small, such that in the next step we can ask the oracle to find a solution of part A. Then we simply apply the algorithm recursively to also obtain an approximate solution for part B. And then in the last step we show that the solution we obtain for part A together with the solution that we obtain for part B is a good approximation of the optimal independent set in the graph. I mean, it's clear that the combination is an independent set because X separates them, but we need to show that it's actually good enough. Now, of course, to be able to show that, we need to pick this separator carefully. Okay, so let's look at what a good separator would be. Okay, so first of all, I said that A has to be sufficiently small to give it to the oracle. So in particular, since this size will determine the size of the kernel, and I promised the size of L squared over epsilon, that means that the size of A has to be bounded by L squared over epsilon. At the same time, I also want that this separator is small, because this separator is basically going to be what we are going to lose, because we never put any of the vertices in the separator into the independent set. So if the separator is large, that would ruin the approximation factor of the algorithm. In particular, we can guarantee that the size of X is at most L plus 1, because the tree width of the graph is L, so we will use one of the bags in the tree decomposition as our separator. Okay, so while we want that A is small, we also want that A is sufficiently large compared to this size of X, such that we can basically bound how much we lose compared to how large the optimal solution will be. Okay, so how can we do this? Well, there's a well-known, I think, theorem that says that if your graph has n vertices and tree width at most L, then it has an independent set of size at least n over L plus 1. There are various ways to prove this. If one looks at an alternative definition of tree width, it is actually immediate. So an alternative way to look at tree width is to say that you can order the vertices of your graph, and then you eliminate them in this order, and whenever you eliminate a vertex, you turn its neighborhood into a clique. And now if there is an elimination order for which whenever you remove a vertex, the size of its neighborhood is at most L, then your graph actually also has tree width L. And from this it's easy to observe that graphs with small tree width have large independent sets, because you can simply greedily in this order add vertices to the independent set and discard the neighborhood, which is always small. Okay, so in conclusion, if the size of A is at least L plus 1 squared over epsilon, then A has an independent set of size at least L plus 1 over epsilon. Okay, so then it has a fairly large independent set compared to the size of X. Okay, so what we want to do is find a node in our tree decomposition such that the size of gt minus xt, so the size of gt without the bag xt itself, is around L plus 1 squared over epsilon, so let's say between L plus 1 squared over epsilon and 10 L plus 1 squared over epsilon. And then A is going to be gt minus xt, and the separator we use is going to be xt. Now there are many well-known theorems about separators in graphs of bounded Treewidth. We proved this one in the paper, but it's really not that exciting. You can simply show that there actually exists a node for which this holds by doing some induction on the tree decomposition. Okay, so we're going to find such a separator. We've shown how to find such a separator such that A has size roughly L squared over epsilon and B is the remainder of the graph. We're going to ask the oracle for a solution in A, then we recurse to find a solution in B. And then it remains to show that indeed if we combine these two solutions, we get the desired kernel. Okay, so let's consider the optimal solution and compare it to the solution that we give. Okay, so if we look at the size of the optimal solution, we can split this into the size of the optimal solution that's in A, the size that's in B, and the part that's in X. Okay, and we can clearly upper bound this by the maximum independent set in A plus the maximum independent set in B plus the size of X. Okay, this may be a very rough estimate, but it's an upper bound. Now, because the oracle is C approximate, we can upper bound the optimum in A by C times the size of SA, and by induction we upper bound the optimum in B by C times 1 plus epsilon times the solution we got in B. And like we've seen previously, we know that the size of X is actually relatively small compared to the size of SA. Okay, so we can upper bound this by C times 1 plus epsilon times the size of the solution we found in A and the solution we found in B. Okay, so the crucial point to getting this to work is that we could split off a part A that was on the one hand small, but on the other hand had a sufficiently large optimal solution. So the crucial point was that we had some sort of lower bound for a maximum independent set on graphs that have low Treewidth. So now I want to look at the approximate Turing kernel for connected vertex cover, and here we actually do not have this property and we need to do a little extra work. So the connected vertex cover problem is given a graph G, you're asked to find a minimum vertex cover in the graph, such that furthermore the graph induced by this minimum vertex cover is connected. Now we cannot apply the idea that we had for independent sets straight away. There is no sort of lower bound for connected vertex cover based on the Treewidth, and also combining solutions in different parts of the graph is more complicated. Let's look into this a little more. So on the one hand, there is no bound depending on the Treewidth, but the problem does have a 1 plus delta approximate kernel of polynomial size for every delta that's a constant larger than 0. So why this is good is because when we try to split the graph into two pieces, previously we just required that part A was small but had a large enough independent set. So right now we cannot say that the graph has to be small but have large enough connected vertex cover, but we just require that it has a connected vertex cover of certain size that's both small enough and large enough, and then we can apply the kernel to ensure that also then the instance becomes small, and if we give that to the oracle, then we again gave a bounded size instance to the oracle. Another problem we have to deal with is that combining connected vertex cover of different parts of the graph is difficult. So if we think about separating the graph into A and B by removing a separator X, it's not the case that if you just take a connected vertex cover in A and a connected vertex cover in B and add the entire separator, that this gives you a connected vertex cover of the entire graph. For normal vertex cover this would work perfectly, but for connected vertex cover it is not. On the other hand, if we look at what an optimal solution of the graph looks like, I mean, this may not be connected when we restrict it to a certain induced subgraph. So we have to deal with that. So first of all, to deal with connected vertex cover, we will use what we call a subconnected tree decomposition instead of a normal tree decomposition. So a subconnected tree decomposition is just a tree decomposition with the additional requirement that GT is connected for all nodes T. Now it's known that you can transform a given tree decomposition into a subconnected tree decomposition in polynomial time without increasing its width. This is sort of natural because you can think that if there's some bag that actually contains sort of two distinct connected components of the subtree, you could sort of split it into two separate bags. It's on the other hand not clear that this subconnected tree decomposition is also a nice tree decomposition, for those of you who are familiar with nice tree decompositions. Okay, so then the idea for connected vertex cover is as follows. First of all, if the graph that we are given already has a sufficiently small connected vertex cover, so say size approximately L squared over epsilon, then what we do to it is we apply this 1 plus delta approximate kernel to obtain a new instance whose entire size is bounded by some polynomial function of L squared over epsilon. Then we give this to the oracle to obtain a solution S prime, and then we use the solution lifting algorithm that comes together with this approximate kernel to find a solution for a graph. Okay, so then we're immediately done. And otherwise, we're going to again sort of split the graph, but we're going to do this in the following way. So let's define, given a graph G and a node T, the following additional two graphs. On the one hand, we define GT hat, which we obtain by taking the subgraph GT and contracting all of xt into a single vertex. And on the other hand, we define GT prime, which is obtained by removing GT for the graph from the graph except for xt, and then again contracting xt into a single vertex. So now what you can actually see is that if you find a connected vertex cover for GT hat and you find a connected vertex cover for GT prime and both contain the vertex z, then you can actually combine them, and then you actually find a connected vertex cover for the graph G where z is contracted into a single vertex. And then you have to do a little bit more work to actually find a connected vertex cover for the graph G, and I'll show you how. So the lemma is as follows. If we have a connected vertex cover in GT hat, then actually we can efficiently find a connected vertex cover in the graph where we again expand this vertex z into the whole set xt. And one can do that in such a way that the size of this vertex cover only increases by at most twice the size of x. Okay, so how does one do this? So we start from some connected vertex cover in GT hat, and it may or may not contain the vertex z. Then we add all of xt to this vertex cover in GT. So now we have a vertex cover in GT, but it's not necessarily connected. So what is the case is that every connected component of this connected vertex, well, not connected vertex cover, contains at least one vertex from xt. So that means that we have at most L+1 connected components. And then it turns out that you can actually efficiently merge two connected components by adding one additional vertex. So if we do this L+1 times, then we've merged all connected components into a single connected component. And the proof for this is as follows. Let's look at two vertices that are in different connected components. And let's just consider the shortest path between them in the graph. I mean, we know that GT is connected, it's just that this vertex cover is not. Okay, now if we look at A prime, which is the last vertex that's in the same connected component as A on the path from A to D, and we look at the next vertex, B, then B is not in the connected vertex cover, because if B would be in the vertex cover, then it would be in the same connected component as A. Okay, but then we see that if we look at vertex C, which is again the next one on the path, this must be in a connected vertex cover simply because it is a vertex cover. And furthermore, C is not in the same connected component as A. So now if we add B to the connected vertex cover, then we've reduced the number of connected components. And if we just keep doing this, then we find a connected vertex cover in GT. Okay, so the overall strategy for connected vertex cover looks as follows. If our graph already has a small connected vertex cover, we could use the 1 plus epsilon approximate kernel and give it to the oracle and then lift that solution back to a solution for G. Otherwise, what we will do, and in the paper we show how you can do this, is find a T such that GT hat has a connected vertex cover whose size lies somewhere between L over delta and 100 L squared over delta, where delta is epsilon over 3, just to allow a little more room for error here. Okay, well then what we will do is obtain a C times 1 plus delta approximate connected vertex cover S hat in GT hat. So GT hat is sort of part A of our graph previously. And we can do that by the 1 plus delta approximate kernel together with the oracle. Okay. And then by the lemma, we transform this connected vertex cover for GT hat to a connected vertex cover for GT that contains all of X. And note now that the size of X is small compared to the size of S tilde. Okay, it's at most a delta fraction by the way that we chose this. Okay, then we obtain a C times 1 plus epsilon approximate connected vertex cover S prime in GT prime, which we just do recursively. And then what we output will be S prime together with S tilde and without vertex C because it's not actually in the graph. Okay, so this is the idea for connected vertex cover. So that leads me just to the conclusion and some future work. So to conclude, we have seen 1 plus epsilon approximate Turing kernels for a whole range of graph problems. And actually, all the ones that are marked in green are captured by our notion of a friendly problem. And we show that all friendly problems have 1 plus epsilon approximate Turing kernels of the following size. And a problem is friendly if, first of all, it has a polynomial size 1 plus epsilon approximate kernel, or a polynomial size exact kernel, of course. It has an approximation algorithm that is sort of good enough, which I won't go into. And it is friendly in the sense that if you have a separator in the graph, then you can sort of easily combine solutions from all connected components of the graph together with the separator to obtain a solution for the whole graph. And that doesn't ruin your approximation factor too much. Now, finally, there of course are many open questions remaining. First of all, you could wonder about approximate Turing kernels for other problems. First of all, to stick to what we were doing, many graph problems are not friendly. So, for example, is there a constant factor approximate Turing kernel for a problem like dominating set parameterized by Treewidth? And of course, you can extend this notion to other parameters, maybe look at other width parameters, because often for width parameters, it can be hard to find polynomial kernels, so that's a good start. And I would also be interested in more lower bounds. Could one prove that the problems for which we've now given 1 plus epsilon approximate Turing kernels don't have 1 plus epsilon approximate normal kernels? And also, is there some lower bounds? Are there some assumptions we can make to get lower bounds for approximate Turing kernels with respect to their size? Right, so thank you for your attention.